Welcome. You're about to use the embedded C creator from TI Electronics. To enable the Debug Monitor or Modbus RTU features, you'll need to purchase our Modbus Dual Masters hardware from the TI Electronics website, as shown in this video. It supports RS485, RS422, and RS232 interfaces. Next, prepare an RS232 to TTL converter, like the one I used from Amazon. If your target device already has an RS232 interface, you won't need the converter. If it supports RS485 or RS422, you can connect directly to the corresponding ports on the Modbus Dual Masters. Purchase the TI Launch XL F2800137 demo board from a distributor like DigiKey or Mouser. Set switch S2's cell 1 to 1. Refer to the image for guidance. SCIA won't appear on the XDS virtual COM port. Instead, it will be routed through the BP headers. Pin 3 of header J1 is SCIA-RX, which maps to GPIO28 on the DSP. Pins 4 and 5 of J1 are SCIA-TX, mapped to GPIO29. Prepare a solderless breadboard and plenty of jumper wires. Connect the RS232 to TTL converter's VCC to the 3.3 volt pin on JP6 of the TI demo board. Connect the converter's ground to the ground pin on JP6. Connect the converter's TTL-RX to pin 3 of J1. This is SCIA_RXD. Connect TTL-TX to either pin 4 or pin 5 of J1. This is SCIA_TXD. To link the Modbus Dual Masters to the RS232 to TTL converter, use a standard DB9 male-to-male cable with pins 2 and 3 crossed. Plug it into both devices. If this is your first time using the Modbus Dual Masters, download the file configtool.zip from the TI Electronics website. Unzip it, then connect the Modbus Dual Masters to your PC via USB. Run configtool.exe. Click the Search COM button to detect the COM port, then click Connect to establish communication. In the UART1 settings, configure the communication parameters between the target MCU and the Modbus Dual Masters. Set the Modbus mode to RTU. Since we're using an RS232 to TTL converter, UART2 settings define communication between Simulink on your PC and the Modbus Dual Masters. This baud rate must match the setting in your Simulink block. UART3 is for Bluetooth communication. If you're not using Bluetooth for debugging or monitoring, you can skip this section. Bluetooth is useful when your PC is electrically isolated from the target system. Once all settings are configured, click Program Config Data to IC. You'll see a progress bar, and a confirmation message will appear once the configuration is successful. Open MATLAB and Simulink. Click Blank Model to start a new project. Click the Library Browser icon. In the browser, locate the Embedded C Creator section. Drag Setup Target into your model. Drag a Modbus Server Debug Setup into your model. Drag Probe into your model. probe is for monitor output port values. Drag logical operator into your model. Set this block to not. Drag delay into your model. Set delay length to 1. Right-click the delay block and select Format. Flip block to mirror its orientation. Drag D out into your model. Drag display into your model. Connect all blocks as I did. Double-click the Setup Target block and set the target platform to TI C2000 based on sysconfig. Double-click Modbus Server Debug Setup and configure the parameters as shown in the video. Make sure max words Q2I by all probe variables use is set to 1 or higher since we're monitoring one variable. Because we're using RS232 for debugging, leave the RS485TXEN name field empty. Just enter 2 double quotes. Double-click the D out block. Set it to use by physical port name and bit number. Set the port name to GPIO-XX. Set the port number to GPIO22. This corresponds to LED 5, green, on the demo board. Save the model as test_blink_ti.slx. Keep Simulink open. We'll switch to Code Composer Studio next. Launch Code Composer Studio version 20.xx or later. Make sure you're using the Theia-based version, not the older Eclipse version. Also, ensure that C2000ware is already installed. From the menu, click File, Open Folder, and choose the directory where you want to create your project. Then go to File, Import Projects. In the dialog that appears, click the Browse button and navigate to the example project in your C2000ware installation. Driver_lib F2800137 Examples, Empty Projects, CCS. Select Empty Driver_lib Project, then click Finish. Double-click the C2000.cscfg file to open the Select Device dialog. Click Confirm to launch the sysconfig interface. Under the System group, click CPU Timer, then click Add to insert CPU Timer 0. Set the emulation mode as you prefer. For the timer period, enter any value for now. We'll fine-tune it later. Enable the interrupt, register the interrupt handler, and enable it in the PIE. If you forget, Simulink will catch the error during the build. Next, click GPIO and add a pin for the LED blink. We'll use GPIO22, which controls LED 5 on the demo board. Set the direction to GPIO output, and under pin mux, configure it as GPIO 22/56. Now go to the communication group and click SCI. Add SCIA. This is used for the Dual Masters debug and monitor tool. Configure the parameters as shown in the video. Make sure Use FIFO is unchecked and enable both RX and TX interrupts. We intentionally configure only RX interrupt. See what happened later. Under System, expand Watchdog. Set the countdown time to a value greater than 100 milliseconds. And make sure Start the Watchdog is checked. Right-click the project name, go to Build Configuration, CPU1_flash. To generate code from sysconfig, you must build the project, right-click the project again and select Build Project. You'll see two unresolved symbol errors. Don't worry, sysconfig doesn't generate the interrupt handler code. These errors will be resolved after the Simulink build. Keep CCS open. We'll return to Simulink next. Back in Simulink, click Tools, Build Embedded Target and open its IDE. Or right-click the canvas and choose the same option from the context menu. In the pop-up dialog, enter 0.5 as the base sample time. Select the folder where your CCS project is located. An error dialog will appear, indicating that the final period for CPU timer 0 must be set to 1 millisecond. It also shows you the formula and the system clock frequency, 120 MHz in this case. Switch back to CCS and set the timer prescaler to 99 and the timer period to 1199. If you're unsure of the system clock frequency, open the clock tree in sysconfig to view all frequency settings. Right-click the project and select Build Project again. This step is essential to apply the new sysconfig settings. Return to Simulink and repeat the build process. Click Tools, Build Embedded Target and open its IDE. Enter 0.5 for the base sample time. And select your CCS project folder. This time, you'll see an error indicating that both S, CIATX, and RX interrupts must be enabled, and the error interrupt should remain disabled. Switch back to CCS. In sysconfig, go to the SCI section. Enable both RX and TX interrupts, and make sure the corresponding PIE interrupts are also enabled. Click Menu Project and Menu Item Build Project. Back in Simulink, repeat the build process one final time. This time the build should complete successfully, and you'll see a pop-up window indicating that Build Successfully and CCS is running. If CCS was closed, it will reopen automatically. We recommend keeping it open throughout the process. Switch back to CCS. Click Menu Project and Menu Item Build Project. Once the build succeeds, connect your DSP demo board via USB. DSP demo board will power on automatically. Right-click the project and select Flash Project. This will program the DSP's flash memory. After flashing, you should see the green LED 5 on the demo board blinking every 0.5 seconds. Return to Simulink. Set the simulation stop time to infinity for continuous monitoring. Unplug the DSP demo board to power it off. Wait 2 seconds, then plug it back in to power it on again. Click the Run button in Simulink. You'll see the display block alternate between 0 and 1 every half seconds. If you like STM32Cube platform, double-click the Setup Target block and set the target platform to STM32 based on STM32Cube MX. Double-click the D Out block. Set the port name to D, port number to 6. That's all. In the next video, we'll build a target application for sequence control, just like a PLC. Thanks for watching.